Hot take. Peanut butter on a hamburger. Amazing. Okay. This is an acceleration example for Unit 2. It's number 11.2 here. And we're looking at a baseball game. Remember when baseball was a thing, and then COVID happened, and then like 3 games into the season, all the Marlins got COVID? That worked out. Well, in our game of baseball, a baseball is moving at a speed of 40 meters per second towards a baseball player. So here, let's just draw a baseball real quick. Nice red stitching. Wha-ching! Probably the best picture ever drawn. Okay, so it's moving 40 meters per second this way towards the player. The player swings the bat at it. The ball stays in contact with the bat for 5 times 10 to the minus 4 seconds. So t equals 5 times 10 to the minus 4 seconds. Remember, when we see this times 10 to the minus 4, what that means is this decimal here is going to get shifted 4 places, and that negative is going to be to the left. So 1, 2, 3, 4. So this time can be thought of as being 0.0005 seconds. It's the same thing. This is just nicer for sig figs. And then it moves in essentially the opposite direction. So baseball changes direction at a speed of 45 meters per second. What's the ball's average acceleration over the time of contact? And we're looking at an average here. Technically, this acceleration isn't constant the whole time. When we talk about impulse momentum later on in the year, we'll see why this is the case. But let's just look at an average acceleration here. Now, if we remember, an average acceleration is just equal to a change in velocity divided by an amount of time. So it is just a final velocity minus an initial velocity divided by some amount of time here. So how about this? How about you pause the video for a second, try to work out what this acceleration will be, and then we'll unpause it and see what you get. That was my funny face. Okay, so based on what we drew here, there is an error that everybody's likely to make. What people are likely to do is they're likely to say that the final velocity is 45. And they're likely to say the initial velocity was 40. And then we'll divide that by 0.0005, which is 5 divided by 0.0005. This is not the right answer. Why is this not the right answer? Well, it has everything to do with the picture we drew. We said initially that the baseball was moving towards the batter at 40 meters per second. What we implied by doing that was that this baseball is initially being pitched at a positive 40 meters per second. When the batter swings the bat and hits the ball the opposite direction, this arrow is now pointing left. Well, if the right is positive, that means the left is negative, which means we don't have 45 minus 40. We have negative 45 minus 40, which is a totally different answer. What we're going to have here isn't 5 over 0.005. What we're going to have is negative 85 divided by 0.005. This will give us our acceleration. A very different answer from previous. This means our acceleration is going to be negative 17,000 meters per second squared, which is a huge amount. But if you think about what's going on with a baseball and how it pops off the bat, it is accelerating that much, but it's only accelerating like that for a very short period of time. Okay, so that's actually how we do this answer. This is our right equational setup. We just need to be very careful on the direction of things, because remember, our velocities that we had are vectors, and our acceleration is a vector as well. It had to get this object moving in the opposite direction it was traveling. But with that, this problem's finished. Play ball.